Okay, so now we are into spherical coordinates. Let me just come up here and remind you. So spherical coordinates, these are the formulas for the change of variables. X, let me just do it this way. Okay, X is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. So this angle right here, so what is rho? Rho is the distance of the point to the origin. Phi is the angle that the point makes with the z-axis. And then theta, that's just the angle from polar or cylindrical coordinates. So if you take a point and you project it down onto the xy plane, the theta that you'd get from that point, if you just did polar coordinates, is what theta is. Or if you were to convert the point xyz into cylindrical coordinates, the theta here is that theta. Okay, so we want to find this integral where E is a part of the ball centered at the origin with radius 2 in the first octant. Okay, so let's look at the ball of radius 2 and then we'll deal with the first octant part. So let's come up with the spherical coordinates for the spherical coordinates region for this ball of radius 2. So the one I'm about to do now, this is just the ball of radius 2. Well, rho is going to go from 0 to 2. Theta will go from 0 to 2 pi because we want the whole ball. That's all the way around. And phi goes from 0 to pi. So that means, so theta goes from 0 to 2 pi because we want the whole circle. Phi goes from 0 to pi because we want to go from here all the way down to the negative z-axis. So by definition, theta is in between 0 and 2 pi, and phi is in between 0 and pi. Okay, so this means we just want everything. Okay, and we want rho to go from 0 to 2. All right, but now notice that we don't want the whole ball. We just want the part that's in the first octant. That's what E is. Okay, so for E, rho is going to stay the same because rho, we still want the part of the ball. We just want this 1/8 of the ball. But rho's still going to go from 0 to 2. Okay, now theta. So theta, since we only want the part of the ball that's in the first octant, that means we only want theta intervals going from, if we were to project the shape into the xy plane, it would just be this quarter circle that's in the positive x and positive y axis. In other words, the first quadrant. Okay, so this means that theta is just going to go, theta is just going to go from 0 to pi over 2. And then phi, since we only want the part of the ball that is above the z-axis, we just want phi to go from 0 to pi over 2. So phi will go from 0 to pi over 2. Okay, so now we're going to convert this integral into polar coordinates. Okay, so we'll do the rho integral on the inside. So rho will go, will go from 0 to pi over 2. We'll do the theta integral next. Theta will go, oh, sorry. What's going on here? Rho's going to go from 0 to 2. That was a weird mistake. Rho goes from 0 to 2. Theta goes from 0 to pi over 2. And phi also goes from 0 to pi over 2. Okay. Now, just like in polar coordinates, we had the r dr d theta, or in cylindrical coordinates, we had the r dz dr d theta. In spherical coordinates, the thing that we integrate against is the following. So the thing that we integrate against is rho squared sine phi d rho d theta d phi. This is just the analogous thing to the r dr d theta. Okay, so whenever you do spherical integrals or spherical coordinates, an integral in spherical coordinates, write down this part after you write this, and then do the function that you're integrating. Okay, so what is the function that you're integrating? Well, x squared plus y squared plus z squared, that is just the distance of the point x, y, z to the origin, but that's what rho is. And so this is going to be rho squared. So this is rho squared. So just like in polar coordinates, x squared plus y squared is equal to r squared. In spherical coordinates, x squared plus y squared plus z squared is equal to rho squared. Let's see if I can denote that here. This is rho squared. It's kind of hard to see, but trust me. Okay, and now this is just a straightforward integral that you can do. Again, it's kind of tedious. Well, even this one isn't so tedious, but there's 3 of them that you have to do. This is straightforward, and you can do this on your own. So now let's look at this one. So now this is a little bit different than what we saw before. So let E be the region that lies between the spheres x squared plus y squared plus z squared is equal to 1, and x squared plus y squared plus z squared is equal to 9. We want to do this integral. And of course, we want to do this, well, not of course, but I'm telling you, we should do this in spherical coordinates. Okay, so the spherical coordinates for this sphere, are the following. These are just the standard spherical coordinates for a ball of radius 1. And if you don't understand this, spend some time looking in the book about it. But rho goes from 0 to 1, the theta goes from 0 to 2 pi, and phi goes from 0 to pi. Now for this is a ball of radius 3, and so the spherical coordinates for this ball are So this rho squared sine phi d theta d phi, you just write this down whenever you do spherical coordinate integrals, and these are the ranges for the theta and phi. Now we need to figure out the x squared plus y squared. So remember, x, if we go back up to the top here, um, x is rho sine phi cosine theta, y is rho sine phi sine theta. So when I square this, this is rho squared sine squared cosine squared rho squared sine squared sine squared. So what happens is there's going to be this rho squared sine squared phi in both x squared plus y squared. So you can factor that out, and that leaves you with cosine squared plus sine squared. And so down here, what x squared plus y squared is in spherical coordinates is going to be rho squared sine squared phi. Okay. All right, and if you didn't follow that, just write out what x squared plus y squared is, do some algebra, and then use the fact that sine squared theta plus cosine squared theta is equal to 1, and this is what you end up with. Okay, and the book I think walks through that a little bit, but just if you didn't follow it, write it out. And so now this is the integral that you have to do. Again, it's a pretty straightforward integral. The only thing that you have to worry about is that when you get to the phi integral, you're going to have to integrate sine cubed phi, or sine squared phi times sine phi. So for that, you want to write sine squared as 1 minus cosine squared, and then you can use u substitution. Okay. But anyways, aside from that, this is a straightforward integral, even if it's tedious. So this is the answer to the problem.